Now we go to pen pipes, beer bottles. It's blow without a dog, like the flute. Closed cylinder, pen pipes, open, closed, same as bottles. Yes, modifier, none, no buttons, tone holes. Yes, okay. It's blow without a dog, closed cylinder, none modifier. Energy in. Yes, maybe I should say that according to this, excitation energy input, that could be an impulse as in a plucked string, white noise as in a recorder, a friction as in a bow string, an oscillation, a bull roarer, yeah, and tonality, non-linear filter as in a string, multipole filter as in a resonator. A little bit complicated stuff. Yeah. Okay. Beer bottles can be modeled as an Helmholtz resonator. The air jet nickel of bottle is working as a mass, as a length. Mass is rho times this mass density times S area and times the length. Yeah, and here is a cavity, volume V, PA, so pressure. So yes, okay. Something is going on here. There's an X, small x here. So the volume is down here is V minus S times X, because some volume is reduced. Yes, okay, and then the power, the pressure is growing. It's now becomes PA plus P. You have a mass spring. This is a mass, the neck, and the cavity is like a spring. And we have this, we know from the theory, also fundamentals and acoustic, architectural acoustics, that F is C square root, no, sound of air, and divided by 2p times this square root. S is the area of the neck divided by volume of the bottle and times the length of the neck. Yeah. And LE is the effective length of the neck, and this effective length, which is in a denominator in the square root. See the speed of sound. Yes, this formula here is the same as written in chapter 4 in fundamentals, whereas we are talking about the resonance frequency F0. Here it's called F. Yes. Then it's below open closed cylinder. It could be here. Up here it was a closed cylinder with a bottle. Here can be open or closed. Yes, and yes, same principle as a flute, open closed, and you can blow in the nose. Is a little bit special, and I don't know this numbers, what it is standing for. Okay. And then Persian flute, it's blow like in a flute, closed open cylinder. Yeah, it's build an exercise. Build a simple aerophone with no sound holes. Okay, I will use my flute. Of course, there are sound holes there in the flute, but aerophone with no sound holes. It's just a simple one. Yeah, it's more funny with a flute. Black box model of aerophone. Tonality. Energy is comes in edge below reeds or lips. Yeah. Typical resonators closed or open cylinders, cone or none. Tone holes, pistons and slide. Okay, something called the scientific approach to tone hole placements is a little bit complicated for me. Acoustic of a pipe, one tone hole correction, yeah. We have here we have acoustic lengths, it's called effective length correction. Is this y is a distance of the hole to the hole of the end of the pipe. Here's a hole to the end of the pipe. A is the radius of the pipe. B is the radius of the hole. T is the depth. Oh, now it comes. T is the depth of the hole. Okay, according to the flute. T is the depth of the hole. T is the depth of the hole. So we have it here. T, E, effective length of the embouchure, T plus 1.5 multiplied with W. T is what is called T is the depth of the hole. Yeah. Now instead of W is B here. Okay. There's a formula for X. This effective length correction is TE, the whole effective length divided by this denominator you can see here. Okay. Yeah. So you can increase the natural frequency by increasing the size of the tone hole. Yes. This function is an approximation for large tone hole diameter. The smaller the ratio B divided by A, the smaller, the further the hole needs to be from. Yeah, if this gets smaller, this fraction in the denominator squared, then x is growing. So x is longer. Okay. Yips. Acoustics of a pipe. Tone hole lattice correction. The effective length will depend on the size of the holes, but also on the other holes. A little bit complicated. We have here again. It's a good. In that way, it's a good figure. Acoustic length, and its acoustic length is the sum of this embouchure. What's called embouchure correction plus the physical length plus this distance from the hole to this distance from the hole to as seen before. X is the end correction from the first open hole. S is the half distance between two holes. A is still the radius of the pipe. B is the radius of the hole. T is the depth of the hole. Yeah, okay. And T is the hole effective length. See here again, and a little bit complicated. What's called formula for X. In English, a little bit complicated expression or term. Yes. Holes, tone holes and blow embouchure holes corrections are a little bit difficult again. Real instrument, physical length, effective length up here is the sum of the mouthpiece. It's called here mouthpiece equivalent length plus the end correction. The effective length is the sum of those corrections and the physical length. Blowhole correction depends on the position of the player's lips, distance and overlap distance from the hole and the overlap. First hole correction depends on hole, tone hole, it's called this bore and positions. Second and other depends also on the number of other tone holes opened. To a recorder fingering chart. It's complicated for me. Dual chord. Okay, here's a C sharp and D sharp, C sharp and D sharp, C sharp and D sharp here. Tone holes for lower notes. Yeps. Then acoustic of a pipe. See here the flute again. Effect of the closed holes. Enlargement factor is EC 1 plus 1 half times this term. S is the half distance between two holes as before. A is the radius of the pipe. B is the radius of the hole. T is the depth of the hole. And C is the hole effective length. Okay. The closed tone holes can be modeled as additional cavity that increase the effective length. Additional cavity that increase the effective length. Okay. The effect can vary in a flute from 2 to 5%. Decreasing T can help to minimize this effect. If T or Te is less, then the effect is less. Flue key pad are never fully open. Effect of closed holes continued. Left little time is 2A is a diameter of the tube. 2S is a double distance between holes. 2B is a what's called the diameter of the hole. X is the position of the first hole. S distance between half distance between two holes. A radius of the pipe, and B is radius of the hole. T is the depth of the hole. T is the hole effect length. So